everyone. So today we are looking to get a little more mathematical about our definition of a derivative. And so we want to kind of start to think about what is this derivative concept that we're chasing. And usually when I teach this in class, I have kind of an interactive demonstration that I do with like a graph applet on the board. I'm going to try to just draw this for you, and I'll start here on the left side of this page. So when we're looking for a derivative, let's just try to remember what it is we're trying to find. So let's suppose that this is our graph that we're working with. Okay, maybe it's an exponential graph, maybe it's a quadratic, I don't know. But and what we really want to know is what is the derivative at this point right here. And remember, the derivative is the slope of the tangent line. So the slope of the tangent line, I don't want to draw it in here because of what I'm about to do next, but it's a line that comes along and touches at just that one point, and the derivative is the slope of that line. The problem we run into is if that line only touches at this one red point, I don't have the 2 points that I need to make a slope. To do y2 minus y1 and x2 minus x1, I need 2 coordinates. So the way this is going to work is I'm actually going to choose another coordinate here. And let's go back to this first point. We're going to call this value here just x. Okay? And then I'm going to say that this other red point is like h units to the right, or it could be h units to the left. It doesn't really matter. So the value of this, or the x value of this red dot, would be x plus h. So h represents the horizontal distance between these 2 points. And I'm going to find a slope of this line, which is technically a secant line because it intersects in 2 points. Okay? Okay, so now to find the slope, my y value here, if this is x, this would be considered to be f of x. And then this point here would be f of x plus h. And so now down below, I'm going to write what this statement would look like if I were trying to find slope of that red line right now. So my slope would look like f of x plus h minus f of x. Those are my 2 y coordinates over x plus h minus x. Okay. There's my slope. One thing you might notice here is down here on the bottom, I have x plus h minus x, so I actually could just get rid of those x's altogether. But now the question is, how do we turn this thing into a tangent line? And this is where having kind of an interactive diagram would probably be more helpful. But what I really want to do is I want to shrink this h value to 0, meaning I want to pull this red point here closer and closer and closer to this red point. Now I can't actually get there. I can't actually touch that point because as soon as I touch it, my line disappears and I only have 1 point to work with. But this is the whole idea we worked with in the first chapter, and let me just sketch a quick picture up here. You don't necessarily have to write this down, but do you remember all those functions we worked with where we had something that looked like this, but at one particular point there might be a hole in the graph? Okay, so that function does not exist at that point, but we can get closer and closer and closer to it for both sides. That's called taking a limit. And we can take the limit and kind of figure out where should this point fall, even if that point doesn't actually exist. And the whole reason we spent so much time on that, by the way, is an indeterminate type situation. The reason we spent so much time talking about that is because of this right here. This is going to be an indeterminate limit. But we are going to work some algebra magic and be able to figure out what would that value be. What is that approaching, even if I can't actually get there? And so what we're doing is we're taking this expression and we're taking a limit as our h value approaches 0. Because 0 is the distance between, h is the distance between these 2 points, and I want to shrink the distance to 0 and see what happens. Okay. There is another way to represent this, and we'll do that in just a second, but I want to go down here to this example 1 and show you how this method works. So it says our function is f of x equals x squared, so that's not quite what I have drawn here, but you know, mathematically it'll still work. And I want to find the derivative of this function using the limit definition of a derivative. So this thing that I wrote right here, this is the limit definition of a derivative. Okay, so my f of x is x squared. I'm just going to jot up here that if I asked you what is f of x plus h, that means what we're doing is we're putting x plus h in place of x. So that's going to look like this. And so what we're really doing here is the limit as h approaches 0. And now I'm just setting this thing up. F of x plus h is going to be x plus h squared. And then minus f of x, which is x squared. And on the bottom, it's just going to be an h because, again, we talked about those x's dropping out of there. Now, if I put a 0 in right now, if I plugged in a 0, this thing zeroes out. I end up with x squared minus x squared, which is 0. And then on the bottom, I would have a 0. And I would have an indeterminate limit. So I'm going to kind of follow that strategy that we used before. When we have an indeterminate limit, what do? Well, we ignore the limit and we mess with this thing. And we see if we can simplify this at all. So I'm going to head down here. And I'm going to take my expression off of the limit. And let's see what we can do. Well, x plus h squared, I can FOIL that. So I end up with x squared plus, and you could write this out off to the side if you needed to, but to FOIL this thing, I'm going to have an x times h and another x times h. So that would be a 2xh. And then an h squared, and then minus an x squared still. That's coming from right here. And then we're going to divide by h. Okay, two things you should notice now. First thing is the x squareds disappear, right? I have an x squared minus x squared, so those go away. And then, if I look at the two pieces I have left, I'm dividing by h, which means each one of these pieces is going to lose an h. So I'm going to lose an h here, I'm going to lose an h here, and then that cancels with this h. And so now this expression boils down to just 2x plus h. That's what I have left. And that's what I'm going to carry back up here, and I'm going to say, okay, well, this is the same as if I take a limit as h approaches 0 of this guy, of 2x plus h. Because what I did here is I simplified this expression to turn into this, but in doing so, I got rid of my discontinuity. I got rid of the piece that was not continuous. I have a removable discontinuity here, okay? And now, if I plug a 0 in for h, what I end up with is 2x plus 0, or in other words, just 2x. That right there is my answer. Okay, the 2x is my answer. The way I would actually write it is I would say f prime of x is equal to 2x. And what that means is that anywhere on the function x squared, and this kind of answers this question down here, which I don't know that I'll take the time to write, but if I look at anywhere on the function x squared, if I want to find the derivative at any x value, all I have to do is do 2 times the x value, and that gives me my derivative. Once we do this other method, I'll draw a picture of that down here, and we'll see if we agree. Okay, so that's what's considered to be the original limit definition of the derivative. Okay, there is another way to think about this. I'm going to draw pretty much the same picture here, but I'm just going to label things a little bit differently. Okay, so just for consistency here, I'm going to draw the same picture. I'm going to draw my same point that I want my point of tangency at. But this time, let's pretend that this is an actual number. Like there is a specific number for this point. Of course, right now I'm going to keep it kind of general. I'm going to call this c. But c represents some number. Okay? Which means that this y value is now f of c. So I'm going to pick another point on this function, just like I did before. But this point gets to just be called x, because that's any other point on the graph, right? C is a specific number, x is anywhere else on the graph, which makes this f of x. Okay. And let's set up our same thing. Let's set up a slope definition here. We want the slope between these 2 points. So the slope between these 2 points is f of x minus f of c, that's y2 minus y1, over x2 minus x1, so x minus c, But this time what I want to do is, again, I'm trying to pull these points closer together. I want to know what happens as this point gets closer and closer and closer to this numerical value. So what I'm doing is I'm taking x and I'm bringing it closer to c. So I'm going to say, let's take a limit as x approaches c this time. And again, c is the number where you're actually trying to take a derivative. So this method, I mean, technically both methods work all the time. But this method works best if you do have a specific number in mind. Like if you have a specific numerical value where I want to take a derivative, this method tends to work better. The first method we did gives us a derivative function. So you'll notice that in this next question it says, all right, let's find a derivative of this function, y equals x squared, at x equals 1. That right there is my c value, okay? So real quick before I start, let's just kind of lay out what we have here. I know f of x is equal to x squared. I know that, well, we have x, which is just x. That's a weird way to write it, but you'll see why I'm doing this in a minute. F of c is taking this 1 and plugging it into my x squared, so it's 1 squared, which is 1. And then my c value is just the 1. Okay, so this is one of my coordinates, x comma x squared, and my other coordinate is 1 comma 1. I wrote this out this way because this is a little confusing that these are both 1s. It's just because 1 squared is still 1. Okay, so my slope setup for this guy. We are taking a limit as x approaches c, which is 1 in this case, of f of x minus f of c, which is 1, over x minus c, which is 1. That's my limit setup. So this is f of x, this is f of c, and this is x minus c. Okay, same thing I have up here. Once again, if I plug 1 in right now, I'm going to get something indeterminate. So I need to take that expression off, and I'm going to kind of work it off to the side here. I'm going to take x squared minus 1 over x minus 1 and see what I can do with that algebraically. See if I can simplify something that makes a discontinuity go away. Well, up at the top, I see that x squared minus 1 can factor into x minus 1 times x plus 1, and then over x minus 1. And then my x minus 1's disappear, which right there, that's my discontinuity disappearing. So this whole thing simplifies down to just x plus 1. So I can go back to this expression here and say, okay, now I'm really just going to take a limit as x approaches 1 of the expression x plus 1. And the reason I can get away with that is this really simplifies into this. These two expressions are almost equivalent except for that one tiny discontinuity. And we're ignoring that because our whole goal is to find what are we approaching as we get closer to that discontinuity. So to find this, now I can just plug in 1. So I get 1 plus 1. And my answer is 2. Okay? Which should make sense to us because up above what we found out is that the derivative anywhere is equal to 2 times x. So had I asked this question up above, I would have just taken this x equals 1 and plugged it in here and said 2 times 1 is equal to 2. Okay, so 2 different ways to find the same answer. This one gives you like a derivative machine. This can find the derivative at any x value. This gives you the derivative specifically at 1. So let's see if we can just remind ourselves, what does this really represent here? Okay, what does it tell us when I say the derivative is 2 at x equals 1 or whatever. Okay, so here's our function, right? Y equals x squared. Let me draw it like this. Okay. And I'm going to focus specifically on this question. If I go to where x equals 1, so that would be, let's assume this point here is 1, 1, which is a point on x squared. If I were to draw the tangent line in, and I didn't draw this very well to scale here, but if I were to draw the tangent line in here, what this tells me is the slope of that tangent line would be equal to 2. Okay? Now, what this is telling us is that I should be able to go anywhere on this function. So like, let's suppose I go to, this point here can be -3 comma 9, because -3 squared is 9. Okay. I should be able to take this -3 and plug it in here. 2 times -3 is -6. And then the slope of this tangent line, let's pretend that's a straight line, would be -6. Okay? So what I've just found is a function that will tell me the derivative anywhere on the original function. If all I have to know is the x value. If I'm at 0 and I plug in 0, 2 times 0 is 0, and that should make sense to you because I have a horizontal tangent right here. Okay? So that's what this is really finding for us. This is your derivative factory that spits out derivatives for anything. This is your derivative specifically at this one particular x value, and that's what this second method is mostly used for. Okay, I think that's a really good kind of example of one of everything. So I'm going to leave this video here, and I will pick up a second video to cover the last couple of examples on the next page.